disappearing soils, and we will look to why do they disappear. But first I will introduce a piled embankment to you, which consists of a field of piles, sometimes depending on the country with a pile cap on top. And then comes a reinforcement, usually a geosynthetic, usually first across and then along. And on top of this comes an embankment. And this embankment consists of sand or broken rock or a broken construction material. And sometimes in some tropical countries, tropical soil, that's right. And on top of this comes a road or a railway or any pavement. And within such an embankment, arching occurs, soil arching occurs. And that means that the load tends to be transferred towards the stiffer elements, which are the piles. Well, underneath this reinforcement, the soil tends to disappear. Not always like this. Here we see soil that is really washed away by a flood, and still the piled embankment, it worked still. You see the geosynthetic hanging, sagging between the piles. This was in Malaysia, and there was flooding, and that the soil was washed away. But even if that's not the case, the soil disappears in many cases. And that is because there is underneath this reinforcement, there is often a working platform consisting of a layer of sand to make it possible to install the piles. And that gives a consolidation of the soft soil underneath. And the result is in many cases like this, a gap underneath the reinforcement. And if we would like to do research on this subject, then we need to be able to model that the soil disappears. And many subjects, this is an issue. For example, you can have a consolidation of a layer, like in this case, but you also can have erosion, so some water leakage or some water flow through sand, and when the sand can go anywhere, then it will go there, and that leaves a gap, for example. Or you can have soil that dissolves, like karst stone that just dissolves in water. Or you can have soil that collapses because there are cavities underneath. So there are many causes why soil disappear. And we are talking about that, how to activate disappearing soil in a physical experiment. And I will lead you through doing that on the case of piled embankment. And in this piled embankment, in the research for this piled embankment, we were interested in developing a calculation model to predict this, the strain in a reinforcement. And here you see this strain. The reinforcement sags in between the piles because we have a cavity or a gap underneath, or just some consolidation underneath. And then that causes that the reinforcement gets longer. So we have strain in it, and we want to be able to calculate this strain on the basis of observations in experiments. And now, in the experiments, how do we activate this disappearing soil due to subsoil settlement or consolidation or erosion or dissolution or whatever? Well, one thing that was done in practice, in physical modeling practice a lot, is a trapdoor. So here we see that we have a plate that is segmented underneath the model, and part of that plate just goes down slowly. That is a trapdoor. And here we see some experiments with trapdoors. And these experiments are 2D. So we have a plate in the 2D model, and it just lowers slowly. There are hundreds of publications about this system. Then very nice test setup of Luc Torel in France, and a moving tray for the centrifuge. A lot of piles go through this plate, and the plate can be lowered slowly. So this models the disappearing soil. Many publications, a lot of research, very nice. This case I do not recommend. Here a lot of piles were installed, and then reinforcement, and then an embankment, and then somebody went underneath and dug the soil away. I do not recommend this. This was done in Singapore, I think. But it resulted, maybe it was Malaysia. It resulted in a nice PhD thesis of Le Hello done in Grenoble, and yeah, it worked, of course. Here the soft soil is modeled with peat, done in the University of Kassel in Germany. Several Saaske and Heitz did their PhDs on this subject. They used peat, which is compressible, so no gap occurring, but consolidation or settlement occurring. Then several researchers used some foam. Sometimes, specifically in a centrifuge, they used EPS, but other types of foam were used too. And then both foam blocks and foam grains were used. And of course, no cap is occurring, but consolidation can be modeled more or less. So you have a settlement. This case, Chinese research. On the left-hand side, we see the test I showed you earlier with water, and the test setup where a railway, a train load is simulated very well. They used water bags in between the pile caps, and they were just emptied. The same is true on the right-hand side, also Chinese water bags, a sand embankment on top of it, and the water bags were just emptied. This looks very much like this research, which is not a piled embankment, but a pipe done in our centrifuge in Deltares. There we had a small balloon specifically fabricated for this purpose. It was filled with water. It was attached to the pipe, and then in the centrifuge, it was emptied due to the gravity force, and then a cap occurred. And this modeled the erosion cap that sometimes occurs around pipes. So here we see the pipe through the glass window, and underneath you see the balloon. This was done in Brazil, and this is EPS, and they dissolved this with orange peel juice because EPS dissolves in orange peel juice. Large-scale tests. And this is done currently in France, large-scale tests on piled embankments. And here they use the cardboard, and they just make it wet. And when you make cardboard wet, it Now about our research, which was the basis of my PhD, we had a test box for 1G circumstances with 4 piles in it. And in between it, we had the soft soil, which consisted of a foam cushion that was fully saturated and wrapped so that it was leak-proof. There was a tap attached, and when we opened the tap and pushed the soil, the foam cushion, it looks like this, then it starts consolidating. So when we open the tap, and only then, and we push it, the cushion, and only then the water starts flowing out. So simulating the consolidation of soft soil exactly. And we did the first test in 2009, and the last test we did in April this year. So we are using this test setup frequently for different configurations. So this was a photo of this test setup with this foam cushion of last April, where we did GeoLab experiments. On top of this comes a layer of sand, and then comes a stiff steel frame with a geosynthetic attached. Here you see it come, and we see strain gauges attached to the geocrypt. And in a recent test, we used a steel reinforcement. We did those experiments with German and Polish partners. And then comes the rest of the box, and a fill is installed. In many cases, it was broken, crushed concrete or masonry or some recycled construction material, because that's the most common construction material in road construction in the Netherlands, because we do not have mountains or rocks. In some cases, we used sand. And then a surcharge load was applied using a water cushion. And on top of that, it was locked and closed. And then we were able to supply a surcharge load of 100 kPa. These are tests done already 10 years ago. And later, we increased the height of the test box. And the test goes like this. In steps, we increase the surcharge loads, and we let the foam cushion consolidate. And then in the final phase of the test, we suck the foam cushion vacuum so that a cap occurs and the soil has disappeared. So do it again. So first, the gravity force and the surcharge load gives the consolidation, and then we suck it vacuum and the soil disappears. This water cushion is not easy to make. We did it first ourselves. We painted a watertight, a leak-proof cover on the foam, and it worked more or less 4 times, and then it was leak. And then finally we found a water bed manufacturer who was very enthusiastic to make such a cushion for us. And he's still working for us now and then. He's just a water bed manufacturer and sometimes making very strange cushions for us. These are the recent tests we did. And now we are, for the same GeoLab project, we are also going to do nearly full-scale tests in Germany and Darmstadt. And that's the second part of the same research for GeoLab. And here we make a combination of an elastic support that gives some elastic deflection underneath the reinforcement and the occurrence of a cap. And that works as follows. Here we have the pink layer. We have a rubber, a granular rubber that's able to give some support, but will also deflect. And below that, we have some hydraulic jackups, and we can lower it. And that works as follows. We will first install the sand layer, and then we will decrease the level of the low steel plate, the bottom steel plate where the rubber lies on. So then you see that a cap occurs underneath reinforcement. I made this animation yesterday. So this, I've never seen this before. Here we make the combination of an elastic support in the initial situation and the occurrence of a cap later. And this is what happens in practice in many cases, because you do not lose your subsoil support immediately, But after a while, it often happens because consolidation occurs underneath section piles embankment due to the weight of the sand underneath the reinforcement, or for example, due to water level, groundwater level changes. For example, due to some construction activity close by where the water is drained out. So we have seen several possibilities to have the soil disappeared. You can use a trapdoor. You can just remove it, which I do not recommend. You can use some Peter soft soil, but then you will only have deflection, not disappearance. You can use foam or rubber. You can use water balloons or water sacks, water bags. You can dissolve, like the EPS in the orange peel juice. You can use that soaked foam cushion that is wrapped and leak-proof with a tap attached. And then the last example I showed you was a combination of rubber and a moving platform. So now, so far, how do we induce the disappearing soil? And now we will look at what we would like to measure, and then specifically in the case of a piled embankment. And for this reason, I will explain you some basics of piled embankments. How do we design the reinforcement in such a thing? Because that's less daily design for many designers. And that's done in two steps. What we want is we want to be able to calculate the strain in the reinforcement. Because if you have that and you have the stiffness, then you have the force, and then you can have decide which strength is needed. And that strain in the reinforcement is calculated in two steps. And the first step is that we divide the load into two parts. One part goes to the piles directly. And that's a relatively large part, and that's due to arching. Arching is of great importance in our geoengineering subject, because if you have some element that moves less than other elements in the soil, then the force will go there. So if you have a certain part in the soil that's compacted better than other parts, then the load will go there. If you have a sheet pile wall that is behaving stiffer at some locations than at another location, then the load will go there. And the same is true in a piled embankment. The pile moves less than the area in between, so the load goes there. That's soil arching. And we can measure this. And then in the second part, we will calculate from the other part of the load, B plus C, we will calculate the strain in the reinforcement. So the final load distribution is like this. Because in the second part, it's too far now to explain everything, but the second part of the load partly is transferred towards the piles and partly can rest on the subsoil if it is there. That is C. Now, how do we measure this load distribution? The initial load distribution can be measured with that device A on top of the pile above the reinforcement. And that's not always easy, because in a centrifuge test, you have a very thin layer for the embankment, and a transducer has a certain thickness, so that makes it difficult to measure this. In practice, you have more space, or so that in practice we have installed it in the field and in 1G experiments a lot. Underneath the reinforcement, we measure A plus B. On top of the reinforcement, in between piles, we measure B plus C. Underneath this reinforcement, we can measure C. And this is always difficult because the load there is small and usually decreases. And decreasing load is difficult to measure. It's very important to calibrate the pressure cell for decreasing load if you expect decreasing load. So you always have to calibrate each instrument before installing it. And best to try a load that you expect in the experiment. And if it is decreasing, use decreasing load. Theoretically, it should give the same result, but it is not always the case. Then in the case of our experiments, we also measure the total load on the steel stiff plate underneath the soft soil. The pressure in the foam cushion, C, should be the same as the total force underneath the foam cushion. So different ways to measure the load distribution. So C is measured in 3 ways. It's a total pressure cell underneath the reinforcement, which actually seldom gives good results. We measure the pressure in the foam cushion, in the soaked foam cushion, and we measure the force underneath the steel plate under the cushion. And those two match very well. So here we see some of the transducers installed in our experiments. A total pressure cell on top of the piles above the reinforcement, pressure cells in between the piles. Yeah, and in the left-hand side, you do not really see a photo of the pore pressure transducer in the foam cushion. This is in the field. Here we have 85 centimeter wide pile caps and a total pressure cell of exactly the same size on top of that. That weighs 200 kilos, the pressure cell itself. They work really nice, already 12 years. So here we see some measurements in experiments. And on the horizontal axis, we see the height of the embankment. On the vertical axis, we see the total load that goes to the pile directly. And here we see some predictions. This way we can compare different models with the measurements. I'm not sure what I was going to tell you. These are German experiments, very much the same as ours. That's because they were first and we copied their experiments and changed some details. And here they measured the vertical pressure above the reinforcement if it was there. So these results are without reinforcement, but at the same position. And what we see is that the yellow, blue, and red ones give more or less the same results. And now they repeated the same experiments, but now with a reinforcement. And what do we see? A really different result. We see that the red one takes much more load than the yellow one. And why is this? This is also soil arching, because the reinforcement between two adjacent piles deflects less than the reinforcement in the middle between 4 piles. And if something deflects less or moves less, it attracts more loads. Of course, the piles attract most load because they move least. But the reinforcement at certain places moves less than at other places, so more load is attracted towards that area. So when we did our research, we were interested in how the load is distributed on the reinforcement. That was one of the main things we actually did, and the findings we were able to explain later. And how did we do this? How did we determine which of these will be most applicable? Well, there is a direct relationship between the shape of the deformed geosynthetic and the load that's exerted on it. And when you have a fully uniform load, then the shape of the geosynthetic will be a full parabola, like this. If you have a triangular load, then the shape will be like this. And if you have an inverse triangular load, then the shape will be like this. And we can measure this easily. we can measure the shape of the reinforcement. And so we did. We did this with the water pressure meter in the tube with liquid, so the liquid leveling system. And we also did it with measuring the geosynthetic before and after a test. And then the difference between the shape was like this. And we were able to make cross sections through these measurements. So we were able to compare these measurements with those theoretical shapes. Now the separate point measurements were like this. And here we see that all the measurements are on or outside the green line, which corresponds to the inverse triangular load distribution. We also measured with the scan transducer, we scanned this shape in one direction, and in the other direction we had this shape. So from this, we concluded that all measurements were on the green deformed line or outside. So apparently this load distribution is better than the others. And then we looked in the field. Here we have an exit of a highway, and we have those settlement tubes attached to the reinforcement. The subsoil support disappeared quickly. In this case, there was a thick peat layer and a sand layer on top of it below the reinforcement. And after using the road for, this is the same, another project, also settlement tubes installed coming out at the side of the road. But in the first project, we measured the shape of the reinforcement after using the road for 1.5 years. And this was the result. And we see those 3 piles, and we see the shape of the reinforcement, and the difference between the highest and the lowest point is around 14 centimeters. And from this, it is possible to calculate the distributed loads directly by taking the second derivative. And that results in this. Of course, it's not very smooth, but this is very much more like an inverse triangle than like a uniform load distribution or a triangular load distribution. So we measured the load distribution not by measuring the load, but by measuring the deformation. And so the conclusion is that what we saw already that most load goes to the area between the piles and not in between, and that the load distribution on those strips between piles is more or less like this, based only on deformations, but that's not true. We also measured the vertical pressure in the German tests I showed. Of course, most load goes to the piles, because the piles move least. Yeah, I think I meant that this is the summary. That's so. Oops. These here we measured the deformations with the liquid leveling system, and yeah, the other one we use in experiments. And here we have experience with optic fibers in this same project. I told you these are optic fibers with brags. You see small disturbances in the optic fibers, and you can measure the difference in length between the brags, even in a high velocity. So a passing truck can be measured really nicely, also after years. And these are the systems that we used in the recent ULab experiments. I think I have more pictures about it, but on the left-hand side, we see the X, Y, Z measurements. So they have several optic fibers combined together in one cable. And we installed it just into the sand fill. And then we kept the X, Y, Z. So all the deformations of each point of the optic fiber we can have of the full fill It's really amazing. But I told you already, it's a lot of work, the data handling. The second one is an epsilon sensor there that measures the strain in the soil. So it's just put in the soil, and you see an optic fiber like this. And from this, they calculate, or they can determine the strain in the soil. And the last one, we glued optic fibers on the steel reinforcement in this case, and that gives the strains in the steel reinforcement. This is in the field, same system in the field, X, Y, Z. And here we see it installed in our lab tests. We see the transparent plastic contains the XYZ measurements. So it's relatively flexible and it can follow the scent. And then in between, we see the black-white cables are the strains in the soil. And we installed this at several levels in the scent fill. This is really amazing. And you need a good, the main investment is the data acquisition system, because you really need an expensive device to connect all those fibers to. We used a Luna system, that's most known, and we have a Luna system ourselves. That's a bit old agent and can not do this. This is too much. So we had to hire another one that's able to measure all these optic fibers in this test setup. Now, very simple. This is basically a bicycle gear cable. The first time we used this in our experiments, we just bought all gear cables of all bicycle shops in Delft. And the idea is you have a stiff steel cable in a tube, and the stiff steel cable is pulled out the tube when you have a tensile strain, and you measure the difference between the two. And we have it nowadays in a more professional way, but it is very basic, and it works. Because it is basically difficult to measure strain in a geosynthetic, because the strains tend to be quite large, so a strain gauge will not measure beyond its own rupture strain, and you cannot attach it well to in many cases. Here we attached, we made a device ourselves to measure in the field the strains. Finish in 2 minutes? Yes, I can. These are optic fibers attached in the field. Yeah, we will. These are all strains measured in different directions in the test setup, and that gives different results. You see that in the strips between the piles we have large strains, and at all other locations we have no or nearly no strains. So measuring deformations, we have seen that measuring deformations can give you the distributed load. That's an important thing to take home. You do not always need to measure load. Now, the result of all these results on the piled embankments was this concentric arches model that is adopted, as Miguel told you already, in a guideline and is in daily use now in several countries. And then these were adopted in this guideline. So far, my presentation. I think we will continue at 11. Maybe you. Yeah?